Okay, so some basic stuff from GCSE generally is how we start off with most of the topics. And this idea of the molecular theory of solids, liquids, and gases, that hasn't really changed at all since GCSE. And we're just looking at the same sort of idea where we've got the particles in contact with the solid, that the bonds between them are a lot more loose in liquids and so small that they're negligible or tend towards zero in gases. So we've got the vibrating particles, the relative motion of those. So those all look like good relevant things that most of you managed to put into your notes. So what I want to, I'm going to jump over temperature and absolute temperature for a moment. I want to talk to you for a moment about internal energy. Okay. Now, for the purposes of this, I'm just going to be talking about gases. Okay. And for the just to avoid confusion in the future, there are two different types of gases. There are what we call real gases and ideal gases. As we mentioned in the last lesson, anything that is ideal is a bit of a lie, but I'll come back and give you some definitions about ideal gases, but I'm not talking about ideal gases for the time being. Okay, so for a gas or a liquid or a solid, as I said, just talking about gases for the time being, each of these particles is going to be moving with a certain amount of kinetic energy just due to its mass and its velocity. They won't all have the same kinetic energy because they'll be bouncing off each other and sometimes they'll be going a little bit faster and a little bit slower. But the average kinetic energy, the average kinetic energy is directly proportional to the absolute temperature. We'll come back and discuss what that is in a bit, but the absolute temperature is just like the Kelvin temperature. You heard about absolute zero last year, but I want to talk about gases a bit more before we get into that. So they'll all have a kinetic energy. So this gas will have a kinetic energy, but it must have some other energy as well, because we talked about these forces in between particles here in a solid being very, very strong, here the forces being weaker, and here the forces being weakest of all. We also had the separation between them, that here was as close to zero as possible. Here we had very small, but ever so slightly bigger. And in this case, we got huge big spaces. So there must have been some work done. We've had some force applied through a distance. So whenever we've changed state from like one of these to another, there must have been some extra work done and some extra energy that has been put into this. And we call this the internal energy. So if we've got a gas or any of these things, we've got our total energy. It's going to be equal to the sum of the kinetic energy, can't spell, still can't spell, and the internal energy. Now, you may have seen, and it would be roundabout now in a sort of normal lesson, that I would ask you all to draw a graph for me of, I don't know, heating up a lump of ice and melting it. So let's go with some Kelvin temperatures and let's test you out. So let's say that I had a block of ice at, no, actually, let's just leave it in degree C. it's easier for the time being. So let's say that I started off at about -20, and this is not scaled particularly well, but let's put like 100 there. And if I was to heat this block of ice at a constant rate, you should remember, you should have covered this in chemistry at some stage, that we would get an increase in the temperature up until the melting point of the ice. Then it would continue on at like a constant temperature for a while, and then it would continue to heat up until it reached boiling point, and then it would stay at the boiling temperature until all of that water had evaporated. Now, if we're constantly heating this, well, in this phase, we're putting in some heat energy and we're getting a temperature increase. In this part, where we're melting, we're still putting in some heat energy, but we're not getting a temperature increase because all of that energy is going into what we call the internal energy of that material. So there's still energy going in, the temperature isn't going up, so the kinetic energy isn't going up, but the total energy is still going up. So that's because we've put that energy into an internal energy instead. So let's actually do some calculations with energy. We'll come back and describe these ideas of energy in a little while. So I want to talk to you about two different things: specific heat capacity and heat capacity, because they are very, very closely related to each other, but there is a difference, and the difference is subtle but important. So we got a nice little simulation here that you can have a little play with in a while. But let me just talk you through what this is to start off with. So what we got, I'm not really interested in the olive oil, mostly interested in just the water. So I'm going to take a lump of iron, I'm going to take a thermometer and put it onto my lump of iron. I'm going to take another one and put it into the water. I'm going to heat up the iron. In fact, I'm going to turn on the little energy symbols. I'm going to heat up the iron. You notice these little energy blocks are going into the iron. Oh no! See, once it gets to a certain temperature above room temperature, if I stop heating it, it will slowly give up some energy to the surroundings. And it's sort of a bit like energy diffusion, because it will slowly spread out until the energy concentration or the temperature in the block is the same as the surroundings. But I don't want to do that. I'm going to heat it up as hot as it goes. So some magic temperature, I'm going to call it 1, 2, 3, 4. I'm going to say that it's at 50 degrees just because there are 5 little divisions on here. And I'm going to take this and drop it into the water. Splash. And you'll notice losing a little bit of heat energy through the steam, but you'll notice that the temperature of the water and the temperature of the iron block are now pretty much exactly the same. And exactly the same at just under 2 big divisions. I'm going to get rid of my iron. I'm going to reset everything. I'm going to take brick instead. Same as before, thermometers in both, heat it up. Sorry, let's turn our energy symbols on. Heat it up. The more observant among you may have noticed something already. So there we go, up to the same temperature as the iron was. drop it into the water, and they go to the same temperature. That's annoying. They're really close. That's not what it's meant to do. Right, let's reset again. Link our heaters, put on our energy symbols, and get our brick and iron. And let's do it a slightly different way. So we got them linked so I can turn them on. You might notice at the very start that the temperatures, the brick and the iron, are the same temperature, but the iron has a whole bunch of energy in it, and the brick doesn't have all that much. And as I put the same amount of energy per second in, notice that the brick is heating up a lot more quickly than the iron. That's a bit weird because it suggests that the amount of energy it takes to make the brick hot isn't nearly as much as the energy it takes to make the iron hot. And that's an important thing whenever we come to look at materials. And this idea of specific heat capacity is like the amount of energy it takes to make something hotter. We've got an equation for it. You love equations, so welcome to your start of a long love affair with physics equations and dimensional analysis. Well, here it is. So we've got our Q is equal to mc delta T. So let me define a few of these terms for you. So Q is going to be our energy, or heat energy in this case, in joules. M is going to be our mass in kilograms. Delta T is our change in temperature. This can either be in degrees Celsius or Kelvin. Probably I prefer Kelvin, but it works for either. You don't always need to convert it. And this C thing is what we call specific heat capacity. And I'm show you how we can figure out what the units are for this. So if we write out our equation, and directly underneath, I'm going to put in the units for the things that I know. So Q, so heat energy, joules. That was kilograms. C, we don't know, so I'm just going to leave it as C. And I'm going to put in our change in temperature as Kelvin because I like Kelvins better. So if I want to find what the units are for C, this equal sign is not just for the numbers that you put in each side, it's also for the units that you put on each side. And this is a really useful, interesting thing that saved my life in exams a few times. That if you know what the units are, you can figure out what the equation is, and if you know what the equation is, you can figure out what the units are. So I'm going to rearrange this to make C the subject. So what joules, I'm going to have to divide by kilograms and divide by Kelvin. So I can say kilograms to the -1, Kelvin to the -1, and those will be our units for specific heat capacity. Units are important. Units are very important. You will lose marks in questions if you're not including units, and they will often give you things like microvolts and milliamps and various other multipliers on those. So just be aware and keep an eye out for them. Okay, so an example question might be that, well, let's just look at your example from yesterday. So let's say a 600-watt kettle heats Let's keep it simple. So 5 kilograms, so that'd be like 5 liters of water, but I'll not mess around with densities and things. Well, let's not say heats, let's say boils. 5 kilograms of water from room temperature. And we might want to know how long does it take, assuming no energy loss. Okay, so that would be a fairly standard sort of a question. And the way that I would approach this is that we extract information from the question. So we've got 600 watts. So power is equal to 600, blah, 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 boils. Okay, so if it's boiling and it's water, we know something about the final temperature. Let's just leave it in degrees Celsius for the time being. From room temperature, it's really hot in my room, so I'm going to say that the room temperature is equal to 30 degrees, just because I'm making up the question. Normally it would tell you, if they ask you, no, in fact, we don't care about room temperature. We'll always tell you what the initial temperature is in physics. In chemistry, they might expect you to have decided what standard temperatures and pressures are. How long does it take, assuming no energy loss? So we had the mass as well, was 5 kilograms. So let's write out the equation that we had. Q is equal to mc delta T. So we're missing some stuff. We're missing C. We don't know what that is. We don't have a P. And we want to find the time, but we don't have the time. So we need to go and do a little bit of dig. So what I've got over here are a couple of tables, sorry about that, that have two different things. So here we've got our specific heat capacities for a whole bunch of different materials. And we've got our units up in the top. That's nice, they agree with me. So let's find water has a specific heat capacity of 4,200. Now we've got, oh no, an energy and a power and a time. If only we had an equation that linked energy and power and time. Should remember that from GCSE, so we can rearrange that. So power times time is equal to our energy. So we can change around. So we've got P times T is equal to MC delta T. And I'm going to pause the video, and I would like you to work out an answer, please.